our dynamic universe. What we will do today is revise graphs of motion, describe the motion of an acceleration time graph, and draw acceleration time graphs from the information obtained from velocity time graphs. Graphs of motion. Note that in the following graphs, A stands for acceleration, V stands for velocity, and S stands for displacement. Just as the area under a speed time graph gives the distance travelled, the area under a velocity time graph gives the displacement. Here are three graphs showing constant acceleration. The first one is an acceleration time graph where the gradient is 0. The second one is a velocity time graph where the gradient of the line is positive and constant. And the third is a displacement time graph where the gradient is both positive and increasing by the same amount each time. Here are three graphs showing constant velocity. The first is an acceleration time graph, and if there is a constant velocity, that means there is 0 value on our AT graph, i.e. no acceleration. For our velocity time graph, we have a 0 gradient, and for our displacement time graph, we have a positive gradient, which is constant. Finally, we have three graphs showing constant deceleration. First, our gradient is 0 again, but we can see we have a negative acceleration rather than positive. For our velocity time graph, we have a negative gradient, and this is constant again. And for our displacement time graph, our gradient is positive, but decreasing by the same amount each time rather than increasing. Here's an example to look at. The following velocity time graph is produced for a moving body. A. Describe its movement at each point, and B. Draw the corresponding acceleration time graph, including values. Let's start with part A. We want to describe the movement at each point in this graph. So let's look at between A and B first. We have a constant acceleration from 0 to 10 meters per second in 2 seconds. We want to be really specific, so we need to include the start and end velocities and how much time passes. Between B and C, we have a constant velocity of 10 meters per second for 2 seconds. And between C and D, we have a constant deceleration from 10 to 0 meters per second in 1 second. From D to E, the body is stationary. We can see there's 0 velocity there, and that's for 3 seconds. Then from E to F, we have a constant acceleration from 0 to 8 meters per second in 2 seconds, but this is in the opposite direction. It's below this 0, it's into a negative, but it's still a constant acceleration, but opposite direction this time. Imagine your car speeding up, coming to a stop, and then going backwards. From F to G, we have a constant velocity of 8 meters per second for 3 seconds in the opposite direction. And from G to H, we have a constant deceleration from 8 to 0 meters per second in 1 second in the opposite direction. Let's move on to part B. We need to draw the corresponding acceleration time graph for the graph we've been given, and we must include the values. So we can't just draw a rough outline of what the graph looks like, we need to actually calculate some values here. Looking at our graph, between B and C, D and E, and F and G, we have a constant velocity, therefore the acceleration is going to be 0. That was for B to C, D to E, and F to G. For all other accelerations, we're going to need to use our equation A equals V take U over T. You should recognise this, but if you can't remember it off the top of your head, it is in your equation sheet. So let's go from A to B first. Our acceleration is equal to our end velocity, which is 10, minus our start velocity, which is 0, divided by the time taken, which is 2. Therefore, we have acceleration of 5 meters per second squared. From B to C, we know is 0. So from C to D, again, we have A equals V take U over T. So that's 0 take 10 this time, because it's a deceleration. And that's divided by 1 this time. It only took 1 second. Therefore, we have minus 10 meters per second squared. From D to E, again, we know is 0, so let's look at E to F. We've got acceleration, our final speed is minus 8, then we take away 0, because that's what we started with, and we divide that by 2, it took 2 seconds. and we get -4 meters per second squared. And we have F to G is 0, and so G to H, our acceleration is equal to our end velocity, which is 0, take away our initial velocity, which is -8. So notice you've got two negatives in there, and that took 1 second. This is equal to 8 meters per second squared. We can see this on the following graph. This is how we would draw this out. So to start with, we have a constant acceleration of 5 meters per second squared here. That's our A to B. This dotted line is a value of 0 for the acceleration, so this section here is B to C. Oh, not that section there, sorry, not the dotted line, that's just showing that it's moving to 0. This between 2 and 4 seconds is B to C. Between 4 and 5 seconds is C to D, and we can see that is -10 down there. Between 5 and 8 seconds, again, that's 0, that is D to E. Just here is our E to F, we can see that's -4 meters per second squared. Again, we've got our F to G here, it's 0, and our final one was 8 meters per second squared, and that is G to H. Hopefully you can see how each of these numbers corresponds to the graph and how it relates to our velocity time graph. I know it's quite small just there, so here it is bigger on the next slide. Let's try some past paper questions now. If a vehicle is travelling in a straight line, and we have some graphs of velocity and acceleration against time shown, which pair of graphs could represent the motion of this vehicle? Let's look at each graph individually. We've got 5 possible answers here, each with a velocity and an acceleration graph. So let's look at A first. If our acceleration increases, just here, then our velocity time graph would have to look exponential. We saw that in an earlier slide. If we've got an increase in acceleration, this is not going to be a straight line. So this is wrong here. You could also look at it the other way around. If you've got an increase in velocity that's a straight line, your acceleration is going to look different from this. It's going to be a flat line just there. Let's look at B. We've got a constant velocity just here, therefore acceleration is 0. We've not got a change of velocity, but this acceleration is just a constant positive acceleration. It needs to be on the 0 line, therefore B is wrong. Let's look at C. We have a decrease in velocity over time there, but our acceleration is showing a positive acceleration. This would be a deceleration. It'd be down here, so this is wrong. Let's look at D. We have a decrease in velocity over time, so our acceleration should be a constant negative acceleration, but it's showing a change in acceleration. Again, similar to A, this one is wrong, so hopefully if we look at E, it's going to be right. We've got a constant decrease in velocity over time, and it's showing a constant negative acceleration just here, so this is correct. So our final answer is E. The following velocity time graph represents the vertical motion of a ball. Which of the following acceleration time graphs represents the same motion? Initially, looking at our velocity time graph, we can see that there is a constant change in velocity over time. If there's a constant change in velocity, this is equal to a constant acceleration. So for graphs A and B, this is a change in acceleration. It's not constant here, so we can say these are both wrong because these are angled lines. We need them to be straight lines. For C, D, and E, we can see these are all showing constant accelerations, so one of these is going to be correct. For between 0 and 2 seconds, we can see that there is a decrease in velocity, so there's going to be a deceleration there. That's going to correspond to graphs C and D because they both show a negative acceleration, so a deceleration. However, E is showing a positive acceleration, so that's going to be wrong. For the second part of the graph, from between 2 and 4 seconds, again, our line is angled down the way, so it's going to be a deceleration again. So between C and D, we can see C has a deceleration again, but D has an acceleration. So D is going to be wrong. C is our final answer. For this question, we have a crate moving up a slope. As the crate is moving up the slope, the rope snaps. The crate the crate, the graph shows how the velocity of the crate changes from the moment that the rope snaps. We need to describe the motion of the crate during the first 0.5 seconds after the rope snaps. So the first 0.5 seconds is obviously between here and here, and we can see that there is a constant decrease in the velocity here. So we can say a constant deceleration from 3 meters per second to 0 meters per second. And it's just worth one mark. This is all we need to write. For the second part of the question, we want to sketch a graph showing the acceleration of the crate between 0 and 1 seconds. We've been given values along the time axis, but we need to put appropriate numerical values along the acceleration axis. So first of all, let's have a little look at our graph that we've been using and work out some acceleration values. Between 0 and 0.5 seconds, our acceleration is going to be equal to v take u over t, as it always is, and that's going to be equal to 0 take away 3 divided by 0.5. This is equal to -6 meters per second squared. And so that's the first part of our graph. The second part, between 0.5 and 1 seconds, is going to be a equals v take u over t again. Our end velocity there is -2. We started at 0, and our time was 0.5 seconds again. This gives us an answer of -4 meters per second squared. We need to put these numbers onto our graph now, so it's easier with graph paper, but I'm just going to put as close as I can. I've got -2, -4, -6 there. Remember, you can't just shove -6 and -4 in without putting it into a proper scale. That's why I've got this -2 here as well. We're starting off at -6 meters per second squared. Make your line straight with a ruler. Mine's going to be as close as possible there. And then we move to -4 meters per second squared. I'm just going to put a little dotted line here to show what's going on. And then we finish at 1 second. There we go. Mine's a little bit wobbly, but yours will be better than that using graph paper and a ruler. An object starts from rest and accelerates in a straight line. The graph shows how the acceleration of the object varies with time. So we can see we've got an acceleration time graph here. We want to work out the object speed at 5 seconds. And to do this, we can work out the area under an acceleration time graph. Remembering this is similar to how we work out velocity under a displacement time graph. So I'm going to label these as 2 different sections to make it easier for myself. We can have A1 and A2, and adding them together is going to make our total area. So we've got A1 here, that's 0 to 3 on our x-axis and 0 to 4 on our y, so just 3 times 4, easy peasy. We've got 12 there, and our second area is 3 to 5 on our x-axis, so that's 2 multiplied by 0 to -2, and that's 2. So we have 4 just there, but remember this 4, this is going to have to be negative because it's 0 to -2 down at the bottom. If you wanted to, you could just calculate the exact areas and then do one take away the other, or we could add them together but making sure you include this negative value with the 4. So 12 take away 4, our final answer is 8 meters per second squared, and so this is B. Here we've got another example, a bouncing ball. When a ball is bouncing, it is constantly changing direction. As it travels downwards, it starts at 0 but accelerates due to gravity, which is increasing its velocity, until it hits the ground and changes direction. As it moves upwards, it has a high initial velocity that slows down to 0 at its maximum height. A velocity time graph for a bouncing ball will show motion both above and below the horizontal axis to show the constant change in direction. This is what our graph would end up looking like, and if you want to see a simulation of this, you can go to the website on this slide. Another example. Draw a velocity time graph for the following scenario. A girl fires a ball vertically into the air from the ground. The ball reaches its maximum height, falls, bounces, and then rises to a new, lower maximum height. Part 1 of the graph is going to look like this. We've got our ball moving upwards, So we've got a positive value for v, but accelerating downwards. That's why it's got a negative gradient there. The second part of the graph is going to show the velocity of the ball just before landing, which is the same magnitude as the initial velocity of the ball. You see we've got u up at the top there, which is our initial velocity, and negative u at the bottom. That's our end speed it's going to reach just before landing. Then we have the velocity of the ball after rebounding, and this is specified in the question. It's less than the initial velocity of the ball. You can see that by these dotted lines here. It's slightly less. And we have, again, a negative gradient there to show it's going to fall again. Directions of travel. In our example, we use the following. 1. Above the horizontal axis is travelling upwards, and 2. Below the horizontal axis is travelling downwards. Be aware that questions may also use the opposite of this, so you really need to pay attention to what's happening in the question specifically. The key thing to remember here is that when the graph crosses the horizontal axis, this means the object has changed direction, i.e. changing from up to down or down to up. The following velocity time graph describes the motion of a ball dropped from rest and bouncing several times. Which of the following statements are true? Before we have a look at the statements, let's go back to our question and think about what's actually happening in the physical world. It's saying a ball is dropped from rest and bouncing several times. So our ball starts up here, it's dropped, and it hits the ground, and it bounces several times. So it's going to go up, it's going to go down, it's going to go up, it's going to go down. And we've got this decrease in velocity because of, that's just how balls work, isn't it? They lose energy as they bounce. Eventually it's going to come to rest on the floor. So this first statement, 1, the ball hits the ground at P. We can see in our little diagram, the ball is initially falling, and that corresponds to the graph we've been given. We've got an increase in velocity until its maximum velocity just before it hits the ground, and that is going to be at P. So this first one is correct. Number 2, the ball is moving upwards between Q and R. We can see on the graph between Q and R here, we have the ball having just hit the ground. So you can see at P, the ball has just hit the ground. It then travels upwards again. This is this part just here, and that does correspond to Q to R. So this is going to be correct as well. Part 3, the ball is moving upwards between R and S. We can see that if the ball is moving upwards between Q and R, it then crosses the x-axis just here. Thinking back, we know that when our line crosses the x-axis, there is a change in direction. So between R and S, that actually corresponds to this next arrow just here. There's a change in direction. It's reached a velocity of 0, so it's reached its peak height, and then it's starting to travel back down again. So this is wrong. So 1 and 2 only, that's going to be D. Which of the following velocity time graphs best describes a ball being thrown vertically into the air and returning to the thrower's hand? First of all, let's think about what's actually happening. Instead of dropping the ball and letting it bounce, the person is throwing the ball upwards. So let's start with our ball travelling upwards, and then it returns to the thrower's hand. So it comes downwards again to the same level. We know that if a ball is being thrown upwards, there must be a high initial velocity. And this already eliminates one of our answers. D is showing an initial velocity of 0, so it's not going to be this one. If the ball is travelling upwards and then downwards, there must be a change in direction. And we know a change in direction corresponds to the line on the graph crossing the x-axis. So straight away we can see the answer is not going to be E, as it doesn't cross the x-axis anywhere in the middle. B and C both look like they might be crossing the x-axis because there's a change there. However, this angle doesn't actually show across the x-axis. It only touches it and then moves away from it. It's showing the ball moving in one direction, slowing, stopping, and then continuing the direction it was before. So we know it's not going to be B, it's not going to be C. What A is showing is a high initial velocity just here. Oh, that's a wonky arrow. A high initial velocity just here, a deceleration until it reaches its maximum point in terms of displacement, and then it is accelerating in the opposite direction. That's what's happening just here. We can see it on both sides of the time axis. So our final answer is going to be A.